When it comes to the concepts of work and energy, the math behind them tends to be a little bit more straightforward than some of our previously learned concepts. We're going to focus on the two main types of mechanical energy. We have gravitational potential energy and kinetic energy. We will certainly look at elastic potential energy, the energy stored in a spring or some kind of like rubber band, something elastic. We'll look at that in the future though. For right now, the concepts are the same. I'd like to focus just on gravitational potential energy and kinetic energy. So if we start with gravitational potential energy, we know that that's based on height. So the more height something has, the more gravitational potential energy it has. It's the same reason why if someone were to drop something on your head, let's say maybe like a penny from about, I don't know, an inch above your head, you're not really scared of it because it's not going to have that much energy. The height is very low. If I dropped a penny from the top of the Empire State Building onto your head and you were on the street below, that's something that's significantly more terrifying. Now the mass is the same, but that height is significantly higher. And that's why height factors into the calculation of gravitational potential energy. Again, if I drop that penny from about an inch onto your head, not that terrifying of an experience, but let's say I dropped an elephant from an inch above your head. Well, the height is the same, but you're probably or hopefully much more terrified of an elephant being dropped on your head, and that's because its mass is so much higher. So the more mass something has, the more gravity is going to pull down on it. And it makes sense because Fg, the weight of an object, equals mg. So the mass certainly has an effect. The height has an effect. And g, which on Earth is 9.81, that has an effect as well. If I go to a planet where gravity is stronger and will accelerate objects faster, they are certainly going to have more potential energy. So if I want to calculate the amount of gravitational potential energy, I simply multiply the mass by the acceleration due to gravity of whatever planet you're on, times the height of the object above some kind of reference point. Mass is always measured in kilograms, acceleration in meters per second squared, and the height above your ground or your reference point in meters. Likewise, if I want to analyze the kinetic energy, it's going to be based on two things. Well, if you have an object that's traveling towards you very slowly, generally not too afraid of it, something like either a turtle or a small elephant. So if they're traveling slower, you're generally not too afraid of them. The faster they get, the more kinetic energy they have, you may want to avoid standing in front of one of these objects. Likewise, the mass of an object will also give it more energy. Think of it in terms of trying to stop an object. Some object is traveling slowly towards you, and it has a low mass, fairly easy to kind of put your hand out and stop it. Now you have something much larger, like let's say a truck or a bus. Even if it's traveling slowly and you try and put your hand in front of it, it's going to be significantly harder to stop that object. The velocity is the same in either case, but a lighter object will require less force to stop, and a heavier object will require more force. So as you can see, the kinetic energy of a moving object is based on both its mass and its velocity. And if you'd like to calculate that energy, you simply multiply half of the mass times the velocity squared. So those are two ways to get the gravitational potential energy and the kinetic energy, the actual amount of energy. Energy is measured in a unit known as the joule, represented with a J. So just to show you a quick example, this is very straightforward. If I have an arrow that's fired, it has a mass of 1 kilogram, it's traveling at 10 meters per second, and it's currently 3 meters above the ground. Well, Eg is just mgh, so I multiply my mass times my acceleration due to gravity times the height. This arrow currently has 29.43 joules of gravitational potential energy. Well, it's also moving, so it has height, but it's also moving, so the kinetic energy equals 1/2 the mass times the velocity squared. So 1/2, 1 times 10 squared will give me 50. It has 29.43 joules of potential energy, 50 joules of kinetic energy. So the total mechanical energy that it currently possesses, the energy that it can use to do work, move an object that it hits, something like that, create sound, 79.43 joules. So I have my total, but I also have my individual amounts. So hopefully you can see that calculating the energy is fairly straightforward. The only other concept we'd like to look at would be the concept of work. Work is just equal to force times displacement times the cosine of the angle. And the angle here is whatever angle is formed between the force and the displacement. And I'll show an example of this in a second. The second definition of work is just a change in energy. If you think back to the concepts we discussed previously, if energy is added or taken away from a system, it seems to magically appear or disappear, then work has been performed. So work is either a change in energy or a force that acts over a given displacement. So let's look at two examples here. I have the same force in both examples, 10 newtons, and the object is moved 10 meters in both examples as a result. In my first example, the force and the displacement are completely parallel. They both act in the same exact direction. In my second example, I have an angle between these two. While the displacement is to the right, the force is acting upwards. There is an angle of 35 degrees between my displacement and my force. So if we analyze both of these, in the first case, my force is 10, my displacement is also 10. The angle between them is 0. If I kind of moved this displacement vector up and overlaid it on top of this force vector, you notice there is no angle between those two, so cosine of 0. When I calculate that, I find that 100 joules of work was performed on this box. It gained 100 joules of energy. You hopefully realize if I pull on this box with a force, it will begin to move. So in this case, I would gain 100 joules of kinetic energy. If I look at this example, same equation, the only difference, because I have a 35-degree angle between the displacement and the force, I just plug in 35 for theta, and I wind up getting 81.92 joules. It's slightly less because I don't have as much force pulling to the right. In this example, all the force pulled to the right. In this example, I had some pulling to the right, but some of that was also used to try and pull the object upward. So a little bit less force acting to the right, so a little bit less work is performed. So the main concept to realize here is this angle is just the angle between your force and your displacement. In an example like this, it's 0. In an example where the force acts one way but the displacement is in the opposite direction, that would be 180 degrees. Anything in between would be the given angle. Don't forget that work is not only this, but it is also equal to a change in energy. So you could also, based on what you're given, calculate it in another method. So here we have a box that is sliding before with some given information, and it comes to rest. So friction brings this box to rest. If we take a look, I have no energy before except for kinetic because I have no height and no elastic compression. So 1/2 the mass times the velocity squared gives me 12.5 joules. Afterwards, it has no energy, it has 0. You should immediately realize, wait a minute, this is impossible, unless work occurred. So I did have a change in energy. I lost 12.5 joules, and that will be the work that was performed. So I can either calculate it using the force and the displacement, as well as the angle between them, or I can simply calculate the change in energy from before and after. Either one of those will give me a value for work. And work, as you can see, since it's just a change in energy, is also measured in joules.